This is the 15th video in a series devoted to complex analysis, and today we're going to look at some results involving analytic functions. So let's recall a couple of things first. So let's recall that f is analytic on a domain D if and only if f prime exists for all z in D, and f prime is continuous on D. And so that's just the definition of f being analytic on D. Then we had this thing called Morera's theorem, which was like a little bit of a classification of analytic functions. It said that if you had f was continuous on D, and then the integral over the boundary of a rectangle of f of z dz was equal to 0 for all rectangles contained in D, then that implied that f was analytic on D. So notice we've swapped out the need for f prime to exist and f prime to be continuous with just f is continuous and then this integral rule. So we're going to start today by proving something called Goursat's theorem, and it's another classification of analytic functions. So what it says is if f is a complex valued function on a domain D such that f prime of z naught, which is defined as normal, so it's the limit as z goes to z naught of f of z minus f of z naught over z minus z naught. And so if that limit exists for all z naught in D, then f is analytic on D. But let's notice that this is part of the definition of f being analytic in the first place. Notice that up here it says that f is analytic if f prime exists and f prime is continuous. So this is just the existence of f prime. So that means the continuity of f prime is kind of freely built into the structure of a complex valued analytic function. Like I've pointed out before, for a function to be analytic, that's a much stronger condition than a function to be differentiable like on the real line. Okay, so let's get to it. I recalled this Morera's theorem because we will use this to prove this result. So let's suppose that we have R, which is a rectangle in D. And the actual statement of Morera's theorem says that the rectangle can have sides which are parallel to the coordinate axes. But I won't write that down because it's a bit wordy. And then now we're going to subdivide this rectangle. So let's do that. And we're going to subdivide it in the following way. So let's put our rectangle on the board first. So let's say this is our rectangle R. So that means if we are doing an integral around this rectangle, we need to orient it. So we'll orient it as normal with a counterclockwise orientation. So the rectangle is this inside stuff, but the boundary of the rectangle is obviously this outside stuff. Okay, and like I said, we want to subdivide it, and so we'll just cut it in half both ways. So we'll cut it in half there, and we'll cut it in half there. And then we'll introduce some orientations to each of these subrectangles. So this one up here will be oriented counterclockwise the whole way. So that means we've got arrows going that way. Then this one right here will be oriented counterclockwise. So that means we have these kind of canceling arrows here. Then we've got one going to the right there. And then likewise, this will be oriented counterclockwise. So we're going up here to the left here to counteract that. This is oriented counterclockwise. So that means we need one to the left here and one down here to counteract that. So when all is said and done, when we've done this subdivision, because of the orientations reversing as we go through each of the little pieces, we have cancellation there. So that's kind of the idea here. But now we can take the integral over the boundary of R. So recall that this is R. And that will be equal to, or let's write it down, f of z dz. And that'll be equal to the sum of the integral over the boundary of these subdivided regions. So let's maybe go ahead and give these subdivided regions some names so we know what we can write down. So we'll call this one R1. We'll call this one R1 prime, R1 double prime, and R1 triple prime. And you might say, well, why am I not just doing R1, R2, R3, and R4? And that's because I'll really want to define R2 to be something else. Okay, so this is going to be the integral over the boundary R1 of f plus the integral over the boundary of R1 prime of f plus the integral over the boundary of R R1 double prime of f, and finally plus the integral over the boundary of R1 triple prime of f. Okay, so that's how we broke this integral over the whole thing as the integral over all of those pieces. And now while we're at it, I'm going to introduce a little bit more notation, and that is for the length of the boundary of the entire thing, and I'll call that L. So let's say L is equal to the length of the boundary of R. So it's like the perimeter of this rectangle. Next up, since this derivative exists, that means f itself is continuous. But since it's continuous on this bounded domain, that means it achieves its maximum or minimum somewhere on that domain. But that means it must achieve one of its maximums or minimums on one of these subrectangles. So what I'm getting at here is if we look at the values of f over all of these boundaries of subrectangles, it will achieve its maximum among one of those on, well, one of those. So let's just assume that the maximum occurs here. So let's, without loss of generality, assume the maximum of the modulus of f of z is here. And that's what I mean by the maximum. With a complex valued function, we have to think about the modulus. So that brings us into the following inequality. So now we'll look at the modulus of this. So it's going to be the modulus of the integral over the boundary of R of f of z dz will be less than or equal to 4 times the modulus of the integral over the boundary of dr1 of f of z dz. And that's because we've replaced the boundary dr1 prime, dr1 double prime, and dr1 triple prime with dr1. And so if we're getting the maximum modulus on this part of the boundary, then doing that replacement, we get this inequality. Okay, nice. And now we're going to take R1 and further subdivide. So let's divide R1 like similarly. So I'll put it like this and like this. And then we'll have to similarly give ourselves some orientations. So I won't fill in all the details, but we get some orientations for that. And then we can name these as we named our original subdivision. So maybe we'll say that R2 is here, and then R2 prime, R2 double prime, and R2 triple prime. And then we play the exact same game, but now with just R2 instead of R1. Well, R2 and its primes. But that means we can replace this integral involving the boundary over R1 with 4 times the integral over the boundary of R2. And so that means that this whole thing is going to be less than 4 times 4, which is 4 squared, times the modulus of the integral over the boundary of R2 of f of z dz. But now we can just continue this process over and over again. So the next picture would look like a subdivision of this guy right here. So we would be subdividing this to make R3, R3 prime, R3 double prime, and R3 triple prime, and we could continue that down the line. But we can continue it n times, and we'll end up with this is less than or equal to 4 to the n, and then the modulus of the integral over the boundary of Rn of f. Great, and that inequality that we've just constructed is the one that we want to hang on to. So the one starting here and ending here. And then another thing worth pointing out is that since L is the length of the boundary of R, then that means that the boundary of R1, for instance, is L over 2. So that's pretty easy to check. And that means the boundary of R2 will be L over 2 squared, and so on and so forth. So that means the length of the boundary of Rn will be our original length over 2 to the n. Okay, so that's another nice fact that we'll need to start with on the next board. Okay, so let's maybe get rid of this. We'll start with this inequality as well as this length of that boundary, and then we'll work towards the end. So in the last board, we constructed the following inequality. So the modulus of the integral over the boundary of our rectangle of f of z dz was less than or equal to 4 to the n times the modulus of the integral of the same function over the boundary of our integral Rn, which was one of the subdivisions at the nth step of our original rectangle. Now let's recall that the length around our rectangle, in other words, the perimeter of our rectangle R, was equal to L, which means that the length of the boundary curve del Rn is L over 2 to the n, just by like some quick arithmetic. Okay, so we haven't used anything about this yet, the fact that we have a differentiable function. And so let's do that. So let's take a z0 from a certain place. So that place will be the intersection as j goes from 1 to infinity of r sub j. So that means it's within the intersection of all of those rectangles. And then we'll also take a zn, and this is going to be any zn inside the intersection as j goes from 1 to n of r sub j. Okay, but notice since we have the nesting of those rectangles, this is just exactly equal to r sub n, like that. Okay, so let's maybe make a picture of what's going on here. So we have like our subdivision going on like this. So it's going up towards the top. So in this picture, since our subdivision is just arcing up and right, the intersection of all of these rectangles will be this corner point right here. But in an arbitrary case, we don't know that this is going to go up and right. This just makes kind of a nice picture. So let's notice that we're in the nth subdivision right here. Then that means that we're pretty close to this point that's in all of them. So that's kind of the point here. Okay, so this guy right here is playing the role of the Zn. It's any point in the nth subdivision. But then this guy right here is playing the role of Z0. It's one that's in all of the subdivisions. But since those are squeezing together, we know that there's a maximum distance between them. And we can write that down pretty easily. So I'll write it down and then we'll talk our way through it. So we have the modulus of Zn minus Z0. So that's the distance between those two complex numbers, or the distance between those 2 points, less than or equal to 2 times L over 2 to the n. Well, the 2 is there just in case these are kind of as far apart as they possibly could be in that general setup. Okay, but given this, we see that as n approaches infinity, we have Zn approaching Z0. Okay, good. So we've kind of bounded how close these types of things are together. Now we're going to use the fact that this is differentiable, and we'll do that as follows. So now let's take a z in our nth rectangle. So it's any z in our nth rectangle. And we know that the modulus of f of z minus f of z0 over z minus z0 minus f prime of z0 will be less than some number which I'll call epsilon n, where epsilon n goes to 0 as n goes to infinity. And that's because as n goes to infinity here, this z is approaching z0. But because this limit exists, we know that this whole thing right here is going to 0 as z is going to z0. That's just the definition of this guy right here. So now we can take this inequality and clear the denominator, if you will, and that's going to leave us with the modulus of f of z minus f of z0 minus f prime of z0 times z minus z0 is less than epsilon naught times the modulus of z minus z0. Okay, but we have a feel for the size of z minus z0 from this discussion up here. So that's going to be less than 2 epsilon n over 2 to the n and then times L. Okay, so now let's hang on to this inequality in our minds, and then we'll finish this whole thing off with an application of Morera's theorem. Okay, so we had this a while ago, and we also had an inequality on the last board, which I don't really have room to write down, but we're just gonna work off this inequality until we go towards the end. And the step that we're going to make here is to add a version of 0. So the version of 0 we add will be the following. So it'll be the integral over the boundary of Rn of minus f of z naught. So that's a constant function, which means the integral over the boundary is 0 because that's an analytic function, minus the derivative of z naught times z minus z naught. So it's going to be that integral over the boundary. But why do we know that that's a version of 0? Well, this is a version of 0 because the inside here is analytic. And whenever you integrate an analytic function over a closed curve, you always get 0. So that's Cauchy's theorem. Okay, so adding that in, we get the following. So that's inside of the modulus. So that means this is going to be equal to 4 to the n times the integral over the boundary of Rn of, so this is going to be f of z minus f of z naught. So that's the thing that we're adding in. And then minus f prime of z naught times z minus z naught dz. The important thing here is that f of z naught is a constant. So the integral, and a constant function is analytic. Likewise, f prime of z naught is a constant. So we have a constant times an obviously analytic function because this is a polynomial. But now we can apply the inequality that we had. So remember we had something bounding this. So in fact, what we do first, kind of before that, is introduce an inequality here and then bring this modulus inside. So that's technically like the integral version of the triangle inequality. But now we can take our inequality, and this is going to be less than or equal to 4 to the n, and then the integral over the boundary of Rn of, now let's replace this with that inequality. So that was 2L epsilon n over 2 to the n, and then we have dz. But now we're integrating a constant function over this closed curve. So that gives us the length of this closed curve times this constant function. So that's gonna be equal to, let's see, we have 4 to the n times 2L squared epsilon n over 2 to the n times another 2 to the n. The other 2 to the n comes from the length of this closed curve. That's why we have an L squared, by the way. But let's notice that this 4 to the n cancels with this 4 to the n, and we have a constant times this epsilon n, and that epsilon n we know to tend towards 0 as n tends towards infinity. So let's look at the extreme left and right hand side of this. And we have the modulus of this integral is tending, or is less than or equal to 0, but it must be positive, so it's equal to 0. So if the modulus is equal to 0, the whole thing is equal to 0. So we have the integral over the boundary of f is equal to 0. But by Morera's theorem, that means that f is analytic. Okay, so let's get rid of this, and we're going to look at a couple more concepts. Okay, now we're going to move into something that's a little bit different, but still related to analytic functions. So let's recall that if f is analytic, then this derivative f prime can be calculated via the partial derivatives as the derivative of f with respect to x, but also as minus I times the derivative of f with respect to y, if you split your complex variable into real parts and imaginary parts. And this equality right here, which we derived earlier, that's called the Cauchy-Riemann equations, or this is like one version of the Cauchy-Riemann equations. So now from here, that kind of motivates us to take these two things which are equal, add them together and divide by 2, and we get a new expression for f prime. So let's do that. So let's note that f prime of z will be the same thing as 1/2 times f prime plus f prime. But the first version of f prime I will use is this, so the partial of f with respect to x. The second version will be this, so minus I times the partial of f with respect to y. But now we can kind of factor the f out of this, and we'll get a differential operator that looks like this. We have 1/2 times the partial with respect to x operator, so that partial derivative operator, minus I times this other y partial derivative operator, evaluated at f of z. So that really gives us some motivation to define the following object. So we'll define the partial with respect to z to be equal to 1/2 the partial with respect to x minus I times the partial with respect to y. So this is a natural definition because this partial with respect to z applied to a function gives us f prime of z, which is the derivative of the f with respect to z. Okay, but now that we have this right here, that provides some motivation to look at the complex conjugate of this. And that allows us to define a new partial derivative operator, which I'll call partial with respect to z bar. So that'll be the conjugate of this. So that'll be 1/2 the partial with respect to x plus I times the partial with respect to y. So what did we do? We just took the complex conjugate there, so our minus I turned into a plus I. So now let's see what this does to an analytic function. So maybe I'll write it like this. So let's observe that if we take the partial with respect to z bar of f of z, assuming f of z is an analytic function, that gives us 1/2 times the partial of f with respect to x plus I times the partial of f with respect to y. Since this is an analytic function, we can replace the partial of f with respect to x with minus I times the partial of f with respect to y. Then we're adding a partial of f with respect to y, so that gives us 0. And that leads us to a nice, tidy, complex form of the Cauchy-Riemann equations. And so it's a form that has maybe as few symbols as possible. And that would be the partial of f with respect to z bar equals 0. Okay, so I like to think of this as a function is analytic if it doesn't contain any components that are equal to z bar. So if you recall way earlier in the course, we showed that z bar was not an analytic function. Even though it's like kind of a simple, nicely defined function, it did not end up being analytic. And it turns out that this equation is telling us that any function that kind of has a piece of z bar in it will not have a derivative equal to 0 and thus will not be analytic. So I guess I should say this is if and only if f is analytic, because if you recall, we had this if and only if statement that a function was analytic if and only if it satisfied the Cauchy-Riemann equation. So this would be our new, like, complex, really efficient version of the Cauchy-Riemann equations. Now that we've got this taken care of, I'd like to show like an expansion of a complex valued function via a Taylor approximation, which is similar to the expansion that you might learn in a multivariable calculus of a two-variable function into a Taylor polynomial. Okay, but let's get rid of this so we can do that. So let's start with a smooth function. So I'll call that f of z. I'll break it into real and imaginary parts as u of xy and v of xy, although we won't really use that. And so by smooth, I mean that u and v are smooth real valued functions, but f as a total function may not be analytic. So that means it may not satisfy the Cauchy-Riemann equations, even though these are like infinitely differentiable and always give you continuous two-variable functions. Okay, so now we'll look at the Taylor series at z naught, which is going to be x naught plus I y naught. And I'm just going to write down the result and then write a couple of steps working through the calculation of the result to see that this really makes sense. Okay, so the result is that the Taylor series f of z can be rewritten as f of z naught. So that would be like the constant term approximation, the 0-degree approximation. And then we'll have the partial of f with respect to z evaluated at z naught times z minus z naught. So that'll be like the linear term in the z naught direction. And then plus the partial of f with respect to z naught, z bar, evaluated at z naught, and this will be z minus z naught bar, and then plus dot dot dot. So what's going on here is this is the linear approximation in the z direction, if you will. Then this is the linear approximation in the z bar direction. So we're thinking about those as like totally different differential operators over here. Okay, so I haven't really motivated that this makes sense, but we'll do a couple of lines of calculation to motivate why this makes sense. Okay, so I'm gonna just bring this f of z naught down, and then I'll rewrite my partial of f with respect to z as this guy over here. So that's gonna give me the following. I'll have 1/2 and then the partial of f with respect to x minus I times the partial of f with respect to y, and then we'll evaluate that at z naught, but I won't write that down because it's getting kind of messy. And then I can rewrite my x, or my z minus z naught as x minus x naught plus I times y minus y naught. Okay, so that's that first term. Then I can do the same thing for this other one using the fact that the partial with respect to z bar is this guy down here. Okay, so that's going to be plus 1/2, and then we have the partial of f with respect to x plus I times the partial of f with respect to y, and then I'll have x minus x naught, and then minus I times y minus y naught because I had to take my complex conjugate over there. And now we just start combining like terms. So I'll underline some things that we need to kind of put together, but I won't underline everything we have to put together. This is really just a matter of like bookkeeping. So we'll want to end up with this guy right here, partial of f with respect to x multiplied to this x minus x naught. So that happens there, and that happens here as well. So we'll do that like distributive rule and then put all those together. And then similarly, we'll want to make sure this partial of f with respect to y combines with this, and this partial of f with respect to y combines with this, and we'll put those together as well. And then when all is said and done, here's what we get after combining all of those like terms. So we get f of z naught plus the partial of f with respect to x evaluated at z naught, and then x minus x naught, plus the partial of f with respect to y evaluated at z naught, and then y minus y naught, and then plus dot dot dot. And this looks like a Taylor expansion that you might see in Calculus 3 of a multivariable function. So that gives us some motivation why this is the correct format for a Taylor expansion of a smooth function in the complex plane with respect to these two differential operators. So now let's look at another result. So here we've got a nice complex form of Green's theorem. So I think we recalled Green's theorem on a previous video, but this has to do with just complex valued functions. So let's suppose that D is a bounded domain and it has a piecewise smooth boundary, which we'll call del D. And g of z is a smooth function on D union its boundary. So that's like the closure of D. Notice that g is smooth. It need not be analytic. In fact, this is not super interesting if it's analytic. Then this complex form of Green's theorem says the integral over the boundary of g of z dz is 2I times the double integral over the region of the partial of g with respect to z bar. So let's just do a gut check here and notice that if g is analytic, the left-hand side is 0 by Cauchy's theorem, And then the right-hand side is 0 because this function in here is 0 by our new complex version of the Cauchy-Riemann equations. So if f is analytic, this is not super interesting. So we're really kind of most interested in the case when g is smooth and non-analytic. And since this is the complex form of Green's theorem, well, our proof will just rely on the real form of Green's theorem. So we will pass to something that looks like a line integral in the real plane. Okay, so let's maybe get to it. So let's start with this right-hand side, so this, or left-hand side, I should say. So the integral over the boundary of d of g of z dz. So that's going to be equal to the following. So that'll be equal to the integral over the boundary of d of g of z dx plus I times g of z dy. And you might say, well, why is that? Well, that's just because kind of notationally, we've been taking dz to be dx plus I dy. So if you want to get technical, this is like a complex differential one form, dz, and it's the sum of these two real forms where we've multiplied the dy real form with I. So that's a little more technical than we need to get. Okay, now we can apply Green's theorem to this. So that's going to give us the integral over the region, so the double integral over the region of the derivative of this guy with respect to x. So that's going to be I times g of z. So that'll be I times the partial of g with respect to x, and then minus the derivative of this with respect to y. So minus the partial of g with respect to y, and then dA. So next up, we'll factor a 2i out of this. And when we factor a 2i out of this, well, this I is gone. So we've got the double integral over d of dg dx, and then plus I dg dy, because 1 over I is minus I, so that cancels this minus sign. But factoring a 2 out means that we need to introduce a 1/2 dA. But now let's notice that this combination right here is exactly the kind of definition of our partial derivative with respect to z prime. So this gives us the result. We have 2i, the integral over d of the partial of g with respect to z prime. I really like this theorem, mostly because I really like sort of Green's theorem and Stokes' theorem and all of the generalized versions of that, but I really like seeing this like complex version in particular. Okay, so let's get rid of this and we're gonna end with one last result. We're gonna finish with something which is called Pompei's formula, which is a generalization of the Cauchy integral formula. And so it has the same setup as Green's theorem, or the complex version of Green's theorem, which we just proved, and we're gonna use it in the proof. So let's see what it says. So we've got g evaluated at w is 1 over 2 pi I, and then the integral over the boundary of d of g of z over z minus w dz, minus 1 over pi, and then this double integral over the region of the partial of g with respect to z bar, and then 1 over z minus w dz. So let's notice if g is analytic, then this guy right here is equal to 0 because the partial of g with respect to z bar is equal to 0. And we just get the Cauchy integral formula. So this really is a generalization of the Cauchy integral formula. So what we'll do here is define a new region d prime, and that new region d prime will be d minus a little bubble which is centered at w. So let's write it like this. So it's going to be minus all z such that the modulus of z minus w is less than or equal to epsilon. And you might say, well, what exactly is that epsilon? Well, we can talk through it verbally after maybe drawing a nice picture. Okay, so let's start our picture down here with the region D. So let's say this, everything inside of this is the region D. So this in particular is its boundary. And then we want to take an arbitrary point W within D. So this is the point W within D. And then our epsilon will be such that if we make a little bubble around this W of radius epsilon, it's totally contained in D. Okay, so taking this subtraction here means we get this region right here, which is shaded in peach, will be our D prime region. So it's this D minus this bubble around W, where that epsilon, like I said, was chosen so that we're inside that D, and that's always possible because D is an open set. Okay, so why did we take this bubble out? Well, we took this bubble out because this integrand here is smooth everywhere on D except for at W, because that introduces a 0 in the denominator here. So that means this integrand here will be smooth on all of D prime because we've taken out an appropriate bubble around this W. So what we'll do here is start with this integral, but instead of integrating over D, we'll integrate over D prime. And we do that because our integrand is now smooth, but if our integrand is smooth, we can apply Green's theorem. Okay, so we've got 1 over 2 pi I times the integral over the boundary D prime of G of Z over Z minus W dz. So now, like I said, we'll apply Green's theorem to this. So notice the 2 and the I will cancel, leaving us with 1 over pi. And then we'll have the double integral of the derivative of this guy with respect to z bar. But notice the 1 over z minus w doesn't have any z bar component. And so the g is the only thing with the z bar component. So you can like write this out carefully if you need to, but it's kind of using the fact, which is going to be a warm-up problem, that the derivative of z with respect to z bar is 0. So that's going to give us the partial of g with respect to z bar times 1 over z minus w, and then dA, where that is an integral over d. So check it out, we've achieved something that looks like this already. And I should say this is the integral over d prime. Okay, so now that we've got that calculated, we can find this line integral right here over the whole boundary by pasting these two things together. So let's do that. So we have 1 over 2 pi I times the integral over d of g of z over z minus w dz. So that'll be equal to 1 over 2 pi I times the integral over the boundary of d prime of g of z over z minus w plus dz plus 1 over 2 pi I, the integral over this bubble right here. Or I guess I should say the boundary of that bubble. So we can write that as the circle z minus w equals epsilon of g of z over z minus w dz. And now we can apply this result up here to this guy. So let's maybe kind of underline this in blue, and we'll use that for this one right here. So that allows us to rewrite this as 1 over pi, and then the double integral over d prime of the partial of g with respect to z bar, and then 1 over z minus w dz. And then we'll calculate that the old-fashioned way just by using a parameterization of that circle. So let's see, this is a fairly simple parameterization which we've used several times already. And that is z equals w plus epsilon times e to the I theta, because it's a circle centered at w with radius epsilon. And here my theta will come from 0 to 2 pi. Okay, great. So now under that substitution or that parameterization, we'll see that my z minus w term will be equal to epsilon e to the I theta. And then my dz term will be equal to I times epsilon e to the I theta. So when we plug those into this integral, we'll get the following. So we'll get plus, and then we'll have 1 over 2 pi times the integral from 0 to 2 pi of g evaluated at w plus epsilon e to the I theta d theta. Notice that the I here cancels the I that was in the denominator here in the last step. The epsilon here cancels the epsilon here, and the e to the I theta cancels the e to the I theta, so we're left with that. But now this equality is true for all epsilon, so that means we can take a limit as epsilon goes to 0. Notice this first guy right here doesn't have anything to do with epsilon, so we have 1 over pi times the double integral over d prime of the partial of g with respect to z bar of 1 over z minus w dz. And then this whole thing in here is going to tend towards g evaluated at w because that epsilon is approaching 0, like I said. So we're just integrating this constant g evaluated at w from 0 to 2 pi. That'll cancel the 2 pi in the denominator and give us plus g evaluated at w, like that. And I guess I should say one more thing. We still have a d prime here, but as this epsilon goes to 0, this region d prime collides into this region d, so this limiting procedure actually takes this prime away. But now if we compare what we have on the extreme left and right hand side of this, we see that we have something set up that can be quickly rewritten to give us this final result, this Pompei's formula. Okay, so that's good. Now let's maybe get rid of this and we'll leave you with some warm-up problems. I've got 3 warm-up problems to leave you with. The first is that the partial with respect to z of z is the same thing as the partial with respect to z bar of z bar is equal to 1. And then that the partial with respect to z bar of z is equal to the partial with respect to z of z bar, which is equal to 0. So this really kind of hammers home the fact that z and z bar can be thought kind of as independent types of variables. Okay, next is to find the partial with respect to z bar of this quadratic polynomial in the variables z and z bar, and then tune the numbers a, b, and c so that this thing is analytic. And then next is a nice classification using these new differential operators of a harmonic function. That is to show that f is harmonic if and only if the second partial of f, one partial with respect to z and one partial with respect to z bar, is equal to 0. Okay, that's a good place to stop.